Alright, so in this video we go over section 12.3 geometric sequences and geometric series. So in this case we are going to define another kind of sequence, in a very similar way that we defined the arithmetic sequence in the previous section. Well, if we recall from the previous video, well, an arithmetic sequence, it's defined by having all the terms to have a common difference between each of them. Now, how are we going to identify a geometric sequence? Well, in this case, we're not looking for a common difference, but rather we're looking for a common ratio. All right, that is, we're going to divide the subsequent term of a sequence by the previous term. So, as an example, in this case, well, the sequence like this one, 2, 6, 18, 54, 162 is a geometric sequence. That's an example, but what's the common ratio? Well, in this case we're not looking for D but for R. 6 divided by 2, that's a 3. 18 divided by 6 is 3. 54 divided by 18, that's a 3. 162 divided by 54, that's also 3. So the common ratio R equals to 3. Alright? So in this case, well, the form of the sequence is the first term, the second term times the ratio. The first term times the ratio, and then the first term times the ratio squared, and then the first term times the ratio cubed, and so on and so forth. So let's do one example in which we are going to show that a given sequence is indeed a geometric sequence, but we need to first define the recursive form of the of the geometric sequence. Well, given the first term, of course, some arbitrary number a, whatever that number is, so the nth term is going to be given by the previous term times the ratio. We multiply by the ratio r cubed, and then we multiply by the preceding one, to get the next term. So in other words, to show that that a given sequence is geometric, what we need to find out is that R, when we divide a sub n over a sub n minus 1, we have to get some R, an integer or a constant. So let's look at this example. So, well, a sub n equals to 3 times 4 to the nth power. A sub n minus 1 3 times 4 to the n minus 1. Okay, so we are going to compute the quantity R equals a sub n over a sub n minus 1. And in this case, we'd better get a constant. So 3 times 4 to the n power over 3 times 4 to the n minus 1. So right away we can simplify the 3's. Alright, and in this case, well, we're going to have 4 over 4 to the n minus 1, 4 to the n rather. What are we going to get next? So notice in this case that the base is the same, 4, and when we have the quotient of two algebraic expressions in which the base is the same, so recall that a of a to the m over a to the n, that's a to the m minus n. All we do is subtract the exponents. So 4 to the n minus negative 1, n minus 1, be careful with the signs. The sign is going to change. The negative sign is going to change the sign of the terms inside of the parentheses. And the 4 to the n minus n, negative times a negative, it's plus 1. So notice how n minus n cancels out, and we get 4 to the plus 1, which is 1, and 4 to the first is simply 4. So the common ratio in this case is 4. Now we need to find the first term. How do we find the first term? Well, evaluate a sub 1, 3 to the 4 to the first, n equals 1. 3 times 4 to the first, which is 12. So a sub 1, or the first term, is 12, and the common ratio is 4. Let's look at how do we represent, or how do we find a formula to find the nth term of a sequence, because you don't want to multiply numbers by some number r, and then, because eventually that's going to get a little bit complicated, I mean, it's going to be kind of a hassle to just multiply by r every single time. And what if I ask you in a question, you're being asked, you're giving like this example, you're asked for the 9th term. Well, that's looking for the 5th, the 6th, it's already a hassle with the numbers, but I mean, what if you were asked to obtain the 378th term? Well, you don't want to do this 378 times, well, minus 474, right? So you don't want to do that. You want to use a formula that you can just plug in n, which is the number of the term that you want. Well, in this case, so just use the formula. Find the nth term of the geometric sequence. So for the nth term of the geometric sequence, we need two elements, a sub 1, that is the first term, and the common ratio. So the first term, a sub 1, is 10. That's fine. But now what about the common ratio? Well, 9 over 10, that's 9 tenths. What about 81 over 10 divided by 9? Let's see if we get the same 9 over 10. So let's see. 81 over 10. We're going to get decimals, don't worry. Divide by 9. And yeah, that's 0.9. 9 over 10 on do math frac. Yeah, that's 9 tenths, 9 over 10. What about the ratio or the quotient of those two numbers? 729 over 100. Right? And actually, let me put parentheses. Okay, let me clear. Open 729 over 100. Close, divide by 81. Oops, open parentheses as well. Over 10.9. Do you see we get the same? So this is r equals to 9 over 10. So we're ready to act over here. All right. So r equals 9 over 10. A sub 1 equals 10. All right. So we're going to go with this expression in this case. Well, so for part A, we got this. A sub n equals the first term times r to the n minus 1. A sub n equals a sub 1, which is 10, times r, which is 9 over 10, to the n minus 1. So that's the expression for the nth term. Well, in this case, they're asking us to find the 9th term of the sequence. So all we do in this case, well, a sub the 9th term, a sub 9, 10 times 9 over 10 to the 9 minus 1. Alright, so in this case, well, what are we going to get? 10 times 9 over 10. 9 minus 1 is 8. And well, in this case, if we use a calculator, let's see what we get. So that's 10 times 9 over 10 to the 8th power. So we get 4.3046. Well, let's put 4.30467. Well, let's leave it like this. I don't know, maybe MyMathLab is going to ask you for 4 decimal places or 2 decimal places. Well, depending on what MyMathLab asks for. Finally, letter C. Well, for letter C, they're asking us for a recursive formula for this sequence. Okay, so recursive formula, a sub n equals r times a sub n minus 1, and then we also need the first term, a sub 1. All right, so letter C, a sub 1 equals 10, and then a sub n equals, in this case, well, let me write down the formula, r a sub n minus 1. A sub n equals r, which is 9 over 10, times a sub n minus 1. And that's the first term and then the recurrence formula for this. All right, now just the same way we did our arithmetic series, you know, adding the terms of an arithmetic sequence, we're going to do the same to find the terms of a geometric sequence. And well, so again, recall the form of the geometric sequence. You know, you multiply by r and then plus the first term times the not the radius, the common ratio square, and then r cubed, and then so on and so forth. You know, so we're gonna have a sequence of this form. But to find S sub n, you know, like let's say the first 17 terms or the first 32 terms, well, we're gonna use the formula. All we need to know is the first term of the sequence and the common ratio of the sequence. All right. So in this case, what do we want to do? So we have this sequence of given this rule 1/2 to the nth power. They're asking us to find the sum of the first n terms and then use that expression to find the sum of the first 4 terms of the sequence. In a very similar way that we did for the arithmetic sequence, you know, we found a general rule or a general formula to find the first n terms, the sum of the first n terms, and then we wanted to look for the first, I believe I did 67 terms. So in this case, well, for fractions, it's going to be a little bit weird to have that many terms. We're going to have a lot of decimals. So 4 terms is going to be fine in this case. All right, so it would be a good idea to first to expand this sequence, you know, like 1/2 to the first plus 1/2 to the second plus 1/2 to the third plus 1/2 to the fourth, you know, just some terms. Yeah, that's a 1/2 to the n. That's basically what this is. So that's a 1/2 plus 1/4 plus 1/8 plus 1/16. And this would go all the way 1/32, 1/64, 1/128, 1/256, 1/256, 1/512, etc., etc. But we don't want to do all of those, just a few. Enough so we can identify that this is a sub 1, which is 1/2, and the common ratio r equals 1/2 in this case. You know, 1/4, divide that by 1/2, well, we get 1/2. 1/8, divide that by 1/4, you should get 1/2. Actually, if you want to do it in the calculator, let me show you how that works. Why not? So 1/4 divided by 1/2. All right. Oh, wait a minute. No, that's not gonna go. That's not gonna go. So I need to put parentheses. 1/4 over 1/2. 0.5, which is 1/2, right? Let's do the next one. 1/8 over 1/4. 0.5. See what I'm saying? So that's still r. Okay, so let's get the general rule or the formula to find the first, to add the first n terms. That is the first term times 1 minus r to the n over 1 minus r. All right, and of course the radius here cannot be 0 nor can it be 1. You know, otherwise if you divide by 1, I mean, if the radius is 1, 1 minus 1 is 0, the expression is undefined. And well, having a common ratio of 0, it's basically multiplying the first term by 0 to get the next one. That'll be 0, 0, 0, 0, 0, 0, of course. But when it comes to trying to find the common ratio, can we divide 0 by 0? No. 0 by 0, no. It's not going to work. Yeah, well, later in calculus, that's going to make a little bit more sense about what to do when we have that situation of the 0 over 0, but that's coming up later in your math courses. All right, so S sub n, it's the first term, which is 1/2 times 1 minus 1/2 to the n over 1 minus 1/2. All right, so what is this going to be? S sub n equals 1/2 times 1 minus 1/2 to the nth power, and then 1 minus 1/2 is also 1/2. Yeah, this is gonna look a little bit ugly if you think so. Well, cancel, cancel. And S of n equals to simply 1 minus 1/2. I mean, in particular, what we're doing in order to add the next terms is just to subtract powers of 1/2 to the unit. Okay, so that's the expression to find the first n terms. Now let's add the first 4 terms, like 1, 2, 3, 4. Instead of adding this in the calculator, putting on all of them, let's do S sub n. Well, in this case, S sub 4. All we do is 1 minus 1/2 to the 4th power. Well, and in this case, 1 over 1 minus 1 over 2 to the 4th power, that's a 16. And well, the reason why I wrote it this way, so we have 16 over 16, so we can have a common denominator in this case. And well, 16 minus 1, it's 15, and keep the denominator. All right, so that's how we do another example of adding the first n terms of a geometric sequence. All right, so as opposed to arithmetic sequence, so for geometric sequences, we discussed the infinite series. Well, what about those infinite series? Well, if you recall, well, there were finite sequences and infinite sequences, to determine whether a sequence was finite. Well, you might remember 1, 2, 3, and 4. That's a finite sequence because it stops at 4. But if I said 1, 2, 3, 4, comma, etc., with this I'm saying that the sequence is going on forever. So this is finite, this is infinite. So in this case, for an infinite series, well, we can change the notation of these commas for plus signs to just add all the numbers. But in this case, we're adding all the numbers all the way to the infinite term. Well, that's kind of a weird way, like adding infinitely many terms. Well, we use this powerful formula and this powerful idea that is going to allow us to add the infinitely many number of terms. But in this case, well, so when given a series, we need to look for R, all right? That is the common ratio. So in this case, a series will converge to or reach some number. That's what we mean by converge, or will diverge depending on the value of R. So in this case, if the value of R is the absolute value of R is a number less than 1, then the geometric series converges, and its infinite sum, this S subscript infinity, that's the infinite sum, is given by the first term divided by 1 minus the common ratio. However, if R is greater than or equal to 1, then the series diverges. All right, so the series diverges. I will actually make one example of each. Well, actually, I just typed one, but I'm going to do an example of an example of one that diverges. I'm going to make it up soon. All right, so number 1, let's see, determine whether this geometric series converges or diverges. If it converges, find its sum. All right, if we look at the form, sigma going from k equals to 1 to infinity up 2 times 2/3 to the k minus 1, if we compare with this form, we need to obtain what the first term is, a sub 1, which is 2. and we need to find out what the common ratio R equals to. All right, in this case is 2/3. All right, take the absolute value of 2/3. What's the absolute value of 2/3? Well, that's 2/3. And if you notice, this is less than 1. All right, what do we know about this being less than 1? Well, converges. So this sum converges, all right? This is going to go somewhere. It's going to get somewhere. So let's find out what the sum is, okay? So S sub infinity, that's A sub 1 over 1 minus R. So S sub infinity is or infinite sum, the first term, which is 2, divided by 1 minus 2/3. But what is 1 minus 2/3? Isn't that 1/3? All right, that's a 1/3. And then be careful here, when dividing by 1/3, it's the same as multiplying by the reciprocal, which in this case, that's 6. So that means that if we expand this series all the way to its infinitely many terms, if we add all those infinitely many terms, the final answer is 6. Let me make up another series that is going to be divergent in this case. Well, very similar. K equals to 1. Let's put a 5 times 5/3. 5/3 to the k minus 1. In this case, if we observe, well, A sub 1, the first term is 5, and R equals to 5/3. But if you notice, the absolute value of R, the radius, is greater than or equal to 1, so for this reason, this diverges. Alright, so this one diverges, blows up, this series blows up. Well, what's the difference between these two? So every time you add one more term to the series, notice you're multiplying by 2/3. Multiplying by 2/3 by a number less than 1, you make the series go smaller and smaller every time. But as opposed to multiplying by a number that is bigger than 1, what we're doing in this case is making it bigger and bigger and bigger, going up all the way to infinity. So that's why this diverges or goes nowhere, stops nowhere. Right, so all the way to infinity. A very classical, problem. Well, to show that the repeating decimal point 99999, I mean, these dots indicate that this decimal goes on forever. That equals to 1. So we need a different representation of this number, so we can apply the infinite series test for geometric series to find its infinite sum. Okay, so let's start by rewriting the number 0.999 ... Well, let me add another one that goes on forever. This is gonna be the same. Hopefully we all agree with this. 0.9 plus 0.09 plus 0.009 plus 0.0009 plus ... Alright, that's going to go on forever. If we combine these numbers, we should get this decimal. Changing these to fractions, 0.9, that's basically 9 out of 10. This 0.9, that's basically 90, or rather 9 out of 100. 9 out of 1,000. 9 out of 10,000. And this goes on forever. Alright, so what do we have here? The first term, A sub 1, to be 9/10. And then the common ratio, let's divide 9 over 100 by 9/10. Well, let's use our graphing calculator to find this common ratio. Okay, let's find what the common ratio is. So 9 over 100 close parentheses, divide by 9 over 10. 0.1, that is 1/10. All right, let's do the next one. So that's an open parentheses, 9 over 1000 divide by 9 over 100. Close parentheses, 0.1, which is 1/10 again. So the common ratio for this sequence, or series rather, is 1 over 10. So let's use the formula S sub infinity, that's the first term, over 1 minus the common ratio. All right, and so in this case, the first term, which is 9 over 10, divided by 1 minus 1 over 10. But what is 1 minus 1/10? Isn't it 9/10? And 9/10 over 9/10, isn't that equal to 1? Which is what we wanted to show, that this repeated decimal equals to 1. Now you might want to be careful, just to wrap up this this section, you might want to be very careful about what formula to use. Notice we have the formula to find the infinite sum, and we have a formula to find a finite sum. All right, so that's going to depend on the wording of the problem. Maybe you just want to find the sum of the first 75 terms, well, use this formula. You want to find the sum of all the terms, of all the infinitely many terms, use this formula. All right, so that's it for this section. So it's a good place to quit. I'll see you in the next video.